Hi, this is Dr.G.Vikas Paul. In this session, we'll discuss about the propped cantilever beam. So, what is the difference between cantilever beam and propped cantilever beam? A cantilever beam is a beam with one end fixed and other end free. A propped cantilever beam is a beam with one end fixed and other end provided a simple support in order to resist the deflection. The simple support may be roller support or a hinged support, pin support. So if you take for a one end propped cantilever beam with one end fixed and other end roller support, for that a degree of static instability is total reactions minus equilibrium equations. So 4 minus 3 equal to 1. Total number of reactions 4. How 4? At fixed support it is 3 and roller support it is 1. So total 4 minus equilibrium equations 3. So 4 minus 3 1. Degree of kinematic interdependency formula is 3j minus r. Joints 2. So 3 to 2 minus total number of reactions 4. So degree of kinematic interdependency is 2. Okay, if you see for hinged, one end fixed and one end hinged, for ds values r minus e. So r is total number of reactions is 5 here. 3 at fixed support and 2 at hinged support. So 5 minus equilibrium equations 3. So 5 minus 3 2. D equal to 3j minus r. 3 into 2 minus 5. So total number of reactions is 5. So 3 into 2 minus 5 1. Okay, now let us see some area and x bar formulas here for different cases. Okay, first case is when the load is at free end for a cantilever beam. The BMD diagram is shown here, WL and L. Here the formula for area is 1 by n plus 1 into L into B. What is n? X power of x. Okay, for example, for first case it is ax plus b. Therefore x power of x is 1. So in the formula 1 by n plus 1 we have to substitute 1. Therefore 1 by 1 plus 1 2. 1 by 2 into L into B. So it is area of triangle is 1 by 2 into L into B. Now centered formula x bar is n plus 1 by n plus 2 into L. So for the first case 1 plus 1 plus 1 plus 1 divided by 1 plus 2 into L. So 2L by 3. Similarly for second case it is UDL. You can see the bending moment there, WL square by 2. There 1 by 2 plus 1 into L into B means 1 by 3 LB. Here 2 plus 1 by 2 plus 2 into L, 3L by 5. Why n equal to 2 here? Because it is ax square plus, it is in the form of, it is parabola, no? Therefore ax square plus bx plus c. So power of x is 2. Therefore n equal to 2 in the second case. For third case it is cubic, n equal to 3. Therefore 1 by 3 plus 1 into L into B, 1 by 4 LB. 3 plus 1 by 3 plus 2 into L, 4L by 5. Similarly, for the fourth case, when there is moment, it is rectangle, area is L into B, and centroid is L by 2. So let us see the first case, cantilever with eccentric load and propped at free end. Okay, propped cantilever beam subjected to, it is a propped cantilever beam subjected to eccentric load. Okay, W, and at a distance, W is the point load, eccentric point load at a distance of A from capital A. So obviously the distance from the B is L minus x, where L is the total length. Okay, L equal to A plus B. So analyze the propped cantilever beam subjected to eccentric point load and propped at free and draw SFD and BMD. Okay, A equal to L equal to A plus B. Okay, draw SFD and BMD for A equal to L by 2 and A equal to L. For A equal to L by 2 case and for A equal to L case, we need to draw SFD and BMD for that also, for that case also. Okay, A equal to L by 2 means it is center. When it is point load is center. A equal to L means when point load is at B. Now first of all we have to check whether it is a determinate or indeterminate structure. So ds equal to r minus c. So our total number of reactions is 4. 4 minus 3 equal to 1. It is indeterminate, therefore it is indeterminate by 1 degree. Now we have to find the proper reaction RB. So remove prop and step 2 in the step 1 remove prop and calculate delta 1. Okay, so that the structure becomes determinate. Now bending moment diagram will be as shown in the figure. Okay, if you remove the prop, so it will be like a cantilever beam subjected to point load at free end. Okay, for this case if we draw the bending moment diagram, the bending moment diagram will be as shown in the figure. Okay, here the delta 1 is the deflection at B. Okay, now the formula according to Moore's second theorem, the formula delta 1 equal to ax bar by ei, where A is equal to half into A into WA, half into A into WA. Okay, x bar is 2 into a by 3 plus L minus a. So you can see the bending moment diagram at right side. This is your bending moment diagram. Okay, WA negative, and okay, the area is half into A into WA. What is x bar? X bar is a distance from B, from deflection. So 2 into A by 3 plus L minus A. So delta 1 equal to, if we substitute these values, there we will get delta equal to WA square by 2 into 2A by 3 plus L minus A divided by EI. In the next step, we need to calculate the deflection delta 2 by removing the load and placing the prop. Okay, you can see the figure here. We have removed the load and we have placed the prop. Okay, now here the deflection, the bending moment diagram is in this form: RBL. L x bar is from B to L by 3. Okay, so delta 2 equal to Ax bar by EI. Okay, so here A, we have calculated A area is half into L into RB into L. Okay, x bar is 2L by 3, x bar from B. Okay, so if we substitute this, we will get delta 2 equal to RBL square by 2 into 2L by 3 into EI. In step 3, equate delta 1 and delta 2. So when we equate, we will get this equation, and W square by 2 into 2A by 3 plus L minus A equal to RB 2L cube by 6. So if we solve it, we will get RB is equal to WA cube by L cube plus 3 by 2A square by L square minus 3 by 2A cube by L cube. This is your RB. So in the proper cantilever beam, our aim is to calculate the prop RB. Okay. So we need to try SFD and BMD for two cases, that is when A equal to L and when A equal to L by 2. So when A equal to L, that means point load is at B. Okay, now we need to substitute A equal to L in RB equation. Then if we solve it, we will get RB equal to W. Okay, so SFD, BMD straight lines we will get. When A equal to L by 2, that is when the load is at point load is at center, then substitute A equal to L by 2 in the RB equation. So then if we substitute A equal to L by 2, we will get RB equal to 5W by 16. So now we can draw SFD and BMD after finding the RB. This will be your SFD. So 5W by 16 minus at B, and at A it is 11W by 10. Now coming to bending moment diagram, we can draw bending moment diagram. So bending moment diagram will be in this form. Okay, so now we don't know where this a point where bending moment is becoming 0. Okay, how to find this? We should equate the bending moment equation between A and C. So we got no RB into x minus W into x minus L by 2 equal to 0. This we need to equal to 0. Then we will get x equal to 4.054. So at this from B, at this point it is a point of contact. This point is called as point of contraflexure. Analyze the proper cantilever beam as shown in the figure. Draw SFD and BMD. So here there is a point load at center 60 kN and a prop reaction we need to find. P we need to find. First step is to check DS equal to 4 minus 3 equal to 1 degree. It is indeterminate structure. In the next step we need to remove the prop and calculate deflection so that the structure is determinate. The bending moment diagram will be like this. If we remove the prop and calculate the deflection delta 1, this is your bending moment diagram. WL, that means 50 into 3. We need to calculate delta 1, that is YB1 here. YB1 formula is Ax bar by EI. So A is the area, half into 3 into 50 into 3. Okay, is equal to 22.5. So X bar from B we need to calculate 2 into 3 by 3 plus 3 equal to 5. So this is your YB1. YB1 will get it as 112.5 by EI. So step 2, remove load and place prop and calculate deflection for this case. Okay, remove load and place the prop. So this will be your bending moment diagram. RB into 6. So YB2 equal to Ax bar by EI. Okay, now area, what is area here? Half into 6 into RB into 6 is equal to 18 RP. What is X bar here? 2 by 3 into 6. So it is 4. So YB2 equal to 72 RB by EI. Step 3, equate YB1 and YB2. So 112.5 by EI equal to 72 RB by EI. So RB you will get as 15.62 kilonewton. So so when you get RB, you can draw SFD and BMD. SFD is at A, B it is 15.62, at A it is a plus 45.32, at B it is negative. So we can also draw the bending moment diagram by taking sections between each span. Okay, so here we need to calculate the point of contraflexure, that is the bending moment where the point where bending moment is becoming 0. So how to get that point? So substitute
mxx between AC. We got one equation now between AC, one mxx equation, rb into x minus w into x minus L by equal to 0. Substitute this to 0, equate it to zeros. Then I will get 8 equal to x equal to 8L by 11. So this is your point of contraflexure. Okay, 3L by from A.